All right. Well, hi, everyone, and welcome to the August edition of Astronomy on Tap. My name is Colin Burke. I'm a graduate student in the Department of Astronomy here at the U of I, and I'll be hosting today. I want to thank you for coming to another virtual edition of Astronomy on Tap. And I want to remind you at any point, please feel free to ask any questions you might have or comments into the YouTube chat. And I'll be reading the chat and I'll forward any questions that come up to our speaker. And remember, there's no such thing as a stupid question, so please don't feel like you're interrupting the speaker. We really want to have as much engagement as possible, even though it's a little bit more difficult over the virtual setting. And we'll also try to leave some time for questions at the end. So thank you, and remember to grab a drink or a snack. And with that, I'll introduce today's speaker. Today we have Professor Decker French. Professor French recently joined us at the Department of Astronomy here at the U of I as an assistant professor. She grew up in Illinois and is excited to be back after completing her undergraduate studies at MIT, her PhD at the University of Arizona, and a postdoc at Carnegie Observatories in Pasadena. Today she'll be speaking about ocean tides and stellar destruction. And with that, I'll hand it off to our speaker.
Okay, thanks, Colin, and thanks everyone for joining us virtually. I'm really excited to talk today about some of the awesome power that tides have, not just on our own planet, but also on celestial objects across the galaxy and the universe. So before everyone gets settled, if you haven't already, grab a beverage. It doesn't have to be a beer, and also some snacks, not just because it's Astronomy on Tap, and even though we can't have it at a bar, we can have some drinks, but also because I'll do a demo of some of these that you can do at home in just a little bit. Let's see. I'm also really excited to be back in Illinois and to have moved to Champaign. I just joined 2 weeks ago officially in the department, so it's exciting to be here, even virtually. All right, so with that, I want to get started and start by talking about tides on the Earth. So tides on the Earth, we see when, let's say you're at the beach and the water will go up at high tide and recede back down at low tide. And these tides are driven by our own moon and the moon's gravity. So to start thinking about tides and the moon, there's lots of kind of three-dimensional things that go on. I'm going to try to gesture with my hands, but also some props. But to start thinking about what's going on, I'm going to pose a question, which you can either answer in the chat or just answer yourself and try to predict what the answer is going to be. But how often do you see low tides on the beach? If you sat at the beach for a long time, how often would you see them? Would you see them once per month, a low tide once per day, or a low tide twice per day? So think about your answer, post it in the chat if you want to compare with other people. I'll give everyone a second to think about how often you might expect to see tides, either if you've been to the beach and tried to find low tides for looking at tide pools or for surfing or anything like that. All right, if you said twice per day, you are correct. We see a high tide and low tide cycle twice per day. So every 12 hours or so, a little bit more than 12 hours for reasons I'll get to later on, you'll see both a high tide and a low tide. So technically this is twice per lunar day, but we'll get to that. And I find this kind of counterintuitive. When I was learning about tides, I always thought, why isn't it once per day? That would make sense, and how I thought about it before. So I want to walk through some of the physics of what drives the tides and why it's you can kind of gain an intuition for why tides happen twice a day. All right. So let me start with a diagram of the Earth and the moon. So this is not to scale. If I were to draw this to scale, it's actually one of the few astronomical diagrams that I can draw to scale on some tiny slides. It would look like this, but it's really hard to draw diagrams on tiny little planets on my slides. So I'm going to show this all not to scale, but envision the planets, about this far apart. The Earth and the moon are about 30 Earth diameters apart. So when the moon's gravity pulls on the Earth, it's pulling harder on the closer side and weaker on the farther side. So basically, the part of the Earth and the ocean that's being pulled the strongest from the moon is the closer side. So to visualize how this translates into tides, we have to do more than just this diagram. We have to think about the Earth, not just in this kind of outside frame of reference where we're looking at it from afar, but how it looks to us as people who are on the Earth in what we call a rotating frame. And frames of reference, whether they're kind of outside or rotating, can be kind of confusing, but this is something that we experience all the time in our daily life. So one of the examples that I like to think about for frames of reference are figure skaters, because they do all these crazy spins and flips and stuff. And so an example of an outside frame of reference is this video where there's an ice skater and she has a GoPro that's kind of just sat on the side of the rink. So we can see her do her spin, her jump. I don't know that much about figure skating. Her jump and her spin from the outside. So this is what we're used to thinking about if we watch figure skating like on TV. But in her frame of reference, what she can show us if she takes the GoPro with her, it looks very different. So this is what a spin looks like in the rotating frame of the ice skater. And so we know this intuitively, that something will look different whether rotating with something or outside. But what it does to the forces and the physics of things like the Earth and the moon and gravity can be a little bit counterintuitive. So let's try to gain an intuition for how that works. So I'm going to stop drawing the moon for a second, but if you visualize it to the right, the forces on the Earth from the moon will look something like this. So it's stronger on the closer side, weaker on the farther side. It kind of points in just a little bit on the sides there. But in the rotating frame, if instead of looking at this from the outside, but looking at it rotating with the Earth, like we experience when we live on Earth, it looks like this. So when we're rotating in the rotating frame, we get these kind of fake forces or fictitious forces that make it look like there's forces coming outwards on the Earth. And so this is why it's a little bit counterintuitive, because on the far side, there's actually this fictitious force that's pointing away from the moon, which is kind of weird to think about. So you have these two forces going out along this kind of the axis that points at the moon. But then on the top and bottom, and also on the sides, these little kind of slight inward tilts of the arrows that you see on the left diagram, when we rotate with the Earth, those tiny forces act to kind of squeeze the oceans on the Earth ever so slightly. So if I were to draw a bunch of tiny arrows, you would wind up with a circle that looks something like this. And so what this does in the Earth is it gives us these two bulges of the ocean where we see high tide and low tide. So you have these two kind of bulges on the close side and also the far side of the Earth. And then on the top and bottom, and also the two sides, you have low tide. This is hard to draw because it's three-dimensional. And what I should have to demonstrate this is like a football or something, but I don't have a football. I am a nerd, so I have a ball of yarn. So imagine something like this, where if the moon is over here, you have the two kind of close and far sides of the oceans that are bulging out like this to make the tides. But you have these low tides on kind of the top and bottom and also the sides. So what happens is that as the Earth spins, the Earth is spinning around these bulges caused by the moon and experiencing a high tide and a low tide, and a high tide and a low tide as you get one 24-hour day. This is why it's hard to visualize, because oftentimes you see these diagrams like this, and it's rotating kind of in and out of the screen instead of just around. All right, so another way to visualize this kind of three-dimensional sense is to do a demo. So this is where you want to grab your beer and your snacks or your beverage, and the snacks if you haven't already eaten them. And I'm going to stop sharing my screen so you can see what I'm going to point my camera at. So my lovely assistant, will you be on the screen? Is going to help me out. So grab your snacks and give me just a second to properly share my screen. So I have a little workspace. I'm going to do this on a table or anywhere else. I'm going to take my snacks, and the snacks are going to be the ocean in this demo. Okay. And the beer is going to be the Earth, or your beverage, so a glass or a can of soda or anything like that. And its demo, you're going to be the moon. So I'm the moon, this is the Earth, and this is the ocean. So the ocean is candy because the ocean isn't just a bunch of rock that's solid, like this glass is solid, but it can actually move around. And if you squish any part of it, you see that it kind of presses on the rest of this ocean made out of Skittles. All right, so if I'm the moon's gravity is pulling stronger on the close side of the ocean. So take some of your Skittles or your candies or your beads and move them, a few inches in front. Then the planet itself and then this ocean is over here, they get pulled like a medium amount. So they can go over here. And this far side, they do still get pulled. So pull them just a little bit. So you wind up with something like this. So you've got kind of this oval shape. And so even though the moon's really pulling only in one direction, you still get this kind of high tide over here and high tide over here. So as the Earth spins this way, this bulge in the oceans on both sides will stay. So the moon is going to rotate around very slowly. So it's going to go around once every 30 days, right? Once a month. And this is going to go around once a day. So as this goes around, you get, let's say Mr. Sam Adams over here is going to get high tide, see low tide, see high tide, and see low tide. And then it's going to happen, each day as the moon makes this whole thing progress around. Right, so you can eat your snacks now. There's no more demo to be had for the snacks, and I'm going to take this back so I can put my slides back on. Does anyone have any questions? Does that make sense? Is there something about weird Skittle analogies that is making it more confusing? Now is a good chance to ask some questions about that while I get the slides set up again. So if you got questions, just put them in the YouTube chat.
I'll ask one quick question, Decker. You mentioned something about fictitious forces. Maybe you could explain why they're called that. Maybe explain that a little bit more. Thanks.
Yeah. So let me go back to my diagram with the arrows. So one of the reasons that we call this fictitious forces is the force that's acting on the oceans on the opposite side, where the forces are weak. There's no gravity that's pulling the opposite way. It's really just kind of an illusion that there is a force because the Earth is being pulled more than that. It's kind of like if you imagine like being a kid and your sibling is like pulling you by the feet, right? Your hair is going to get pulled back, right? But there's nothing pulling because of the friction. But there's no one who's like pulling your hair from the other side. It's just the friction plus, the person pulling your feet. It's kind of a weird example, but it's kind of the fictitious forces is a way of saying this isn't the direct force that's acting. It's kind of this force that's appears like it's acting because we've gone into this confusing rotating frame. I will say that this, even though it sounds like something that could be simple, this is actually something that's really hard to develop an intuition for when it comes to the physics of rotating things. This is something that trips up first-year college students all the time, right? You are used to your physics and all this, and then you go and you start learning about rotating frames and physics of rotation and trying to understand things like tops and angular momentum. It's really counterintuitive, even though we have some examples from day-to-day life. And the fictitious forces don't make it easier, but it's a way of describing something that only happens because you have this rotating frame of reference. So maybe that, I don't know, maybe that helps.
Yeah, thank you.
All right, so.
Yeah, we have one question just now from Alex. Question is, how strong are the inward tidal forces on the Earth relative to the outward tidal forces?
Oh yeah, so this is a good question. And it brings up something that I didn't quite explain fully. So the tidal forces are really, really weak. And in fact, one of the things that is confusing about tides is trying to understand why tides affect the oceans, but not lakes. Or, let's say you're on the beach seeing high tide. How come you and your beer aren't rising up several meters like the ocean is? And one of the things that is really important in driving the tides is those slight inward forces on the poles. Let's see, let me go back to my diagram. Oops, I lost my connection to my laptop. Let's see. Sorry, slight technical difficulties on my end. There we go. All right, so how come you don't get tides on lakes and you drink on the side of the ocean? It's because of these slight inward forces on the top and bottom. Because the oceans are more or less all connected in the same body of water, right? The oceans are mostly connected. These forces, even though they're so small, remember these top forces are even smaller than the tidal forces that are creating the bulge. They add up because we have this massive ocean, and they're enough to kind of squeeze the oceans and create that bulge. And actually, most of the kind of the height of that is driven by this effect and not the tidal forces themselves. And so, yeah, to answer your question, the forces themselves are really, really weak. But we'll get to areas where the forces are not so weak in just a second. Yeah, good question. Any more questions? Cool. All right. So let's see. Yeah, one of the reasons that I like talking about tides is that it's something that we experience every day. We know about, you've been to the beach, but it has this kind of complex set of reasons behind it. And one thing, this is weird because this is something that was kind of a scandal in 2011, which would not even register, I think, on the news now. But there was a news show host that caused a scandal by saying, tides go in, tides go out. You can't explain that. And scientists were all upset because we can't explain tides. And someone who's on the news being a public voice shouldn't say we have no way to explain tides. And I think it's super important to ask questions about these things and interrogate, why is someone trying to explain tides in this way? Because this is only becoming more important. If you were at AstroOnTap, I think was it last month, talking about kind of these like anti-scientific sentiments that arise in certain parts of science. Sometimes we think that astronomy is immune to these kind of discussions, but it's really not. And these kind of this need for questioning and being skeptical of what are these sources telling you is important in all aspects of science and what you hear. Even something that seems as kind of mundane, I don't think it's mundane, as the tides that come in and out twice a day. It's funny because I don't think that if someone said this now, it would even make the news, which tells us something about how the dialogue has shifted in our country. But with that, let's talk about tides outside of the Earth. So the tides that the moon is exerting on the Earth are relatively weak because the moon is not very massive. The Earth is also exerting some tides on the moon, but we don't see those as obviously because the moon, it doesn't have an ocean. But there is an example where this is much more strong on our own solar system, which is Jupiter's effects on its moons. So Jupiter has a large set of moons, and what it's doing to these moons is really interesting. So while the moon and the Earth are basically on a circular orbit, it's a little bit out of circular, but it's more or less circular. Some of Jupiter's moons are in these highly eccentric orbits, just enough to make the tides do something really kind of extreme to these moons. So if I draw a diagram of Jupiter and the orbit of one of its moons, because its orbit is so eccentric, it goes closer and farther from the planet every time it makes an orbit. And so when it's closest, it has these tidal forces that then relax as it gets farther from the planet. So this diagram, again, is super not to scale because it's hard to visualize otherwise. But here's a video of what that looks like in the reference frame of that planet and what that stretching kind of looks like. Again, this is not really to scale. So this is what's happening to Io as it goes around Jupiter on its orbit around that planet. And what it does is, because that tide is so strong that it's not just moving an ocean, it's moving the rock that makes up and the magma that makes up Io. What it does is it actually drives volcanic activity on the moon. And we can see this when we look, we see literal volcanoes on Io that are being driven by the tidal heating. And the cool thing that you can do to prove to yourself that tidal heating does do something is try to convert this mechanical energy of stretching into heat using a paperclip. If you don't have a paperclip, think about this next time you see a paperclip and want to destroy it. But what you can do is, if you take a paperclip and just bend up one of the sides so you can move it, you can feel it, it's room temperature. If you kind of bend it back and forth, even 5 or 6 times, give it some good bends, it will actually be hot to the touch, just from the energy you put in 5 or 6 bends. So that's what Jupiter is doing to Io, is kind of bending the planet. It's with its tides, causing it to heat up some of the rock and driving this volcanic activity. All right, so I have another question, which anyone can answer, but this is especially if you are here to get extra credit for Astro 210. And so we know that if you think about this, the tides should be stronger when an object is closer to whatever is driving the tides than farther. So for example, if the moon was really far away, you might expect that the tides wouldn't be so strong at all. But how does that force scale? If the moon is twice as far away, how much stronger or weaker would the tides be? So 3 possibilities. Does it scale as 1 over the distance? So that would mean that if the moon is twice as far away, the force would be half as strong. Does it go as 1 over r squared, which would mean that if the moon was twice as far away, the force would be 4 times weaker? And is it 1 over r cubed? So twice as far away, the force would be 8 times weaker. So think about this. I think Gotham will tell you the right answer in your next Astro 210, and maybe discuss why that is. And if you really want to know the answer, ask me afterwards and I'll tell you the answer. All right, so moving on. So we can see how tides drive these crazy volcanic forces on Io. But at some point, can the tidal forces be stronger than the gravity that's holding the object together? For Jupiter and Io, fortunately for Io, this isn't the case. Io, the gravity that's holding Io together is so strong that it would be very hard for Jupiter to tear it apart. This isn't the case for something like a supermassive black hole. And actually, one of the coolest things that I think is coming out of modern astronomy is that we're seeing stars get ripped apart by supermassive black holes from these tidal forces. So this is kind of the super extreme end of tidal forces, where if those tides are stronger than the gravity that's holding even a star together, it can rip it apart and accrete it onto the supermassive black hole. All right, so I will give the caveat that I'm going to show a bunch of these pretty images. These are illustrations. Someone has drawn this based on the physics that we think is going on and some simulations that I'll show a little bit later. But this isn't what we see. I'll show you what we see in a second. It's a lot less flashy on a slide.
We did get one other question from Alex, if I could interrupt. The question is, do volcanoes created from tidal heating occur preferentially in certain locations on a moon surface?
Ooh, this is a good question. So for Io, I don't think they do. I'm not an expert in Io, but I believe that because Io has its own rotation, the volcanoes tend to be fairly spread around. But this is something that we can discuss more later, because I would have to look that up in more detail, because someone might have found that there is a preferential side. I don't know the answer to that, but that's a good question. All right, so if you have a star that gets close to a supermassive black hole, you start to get this tidal stretching. So in this picture, you see the artist's conception of what that looks like, where the star starts to stretch out. And if that star gets too close, that stretching can just be more than the gravity of the star can handle, and it rips it apart and winds up eventually, about half of it will fall onto the supermassive black hole, and half of it kind of gets flung out into space. So one of the things that we have to think about when we think about supermassive black holes and this kind of stellar destruction and all this is that this is really not going to happen to us. So we don't have to be afraid of supermassive black holes. This is a illustration of what a galaxy would look like from above. There's no way for us to take this image. So this is, I'm gonna take a picture of a different galaxy, but that blue dot is where we would be in our own galaxy. And the center of that bar that's pointed to with the fuchsia arrow, that's the nearest supermassive black hole to us. And the size of that blue dot, that's 200 light years in diameter. That's like the furthest extent that we've been able to send even like radio signals from the Earth, 100 years in either direction, give or take. So the galaxy is a big, big place, and we're nowhere near the supermassive black hole. So we don't have to worry about, in our lifetimes, in anyone's lifetimes, getting sucked into a supermassive black hole. So I just say that because with all the destruction and tearing stars apart, it's not going to happen to us. We don't have to worry about it. We can observe it safely from afar. All right, so this is again, let's see. I'm going to show not an illustration, but a simulation now of what this would look like. So a simulation is a computer setup of, based on the physics that we know about, what we think should happen to a star that comes too close to a supermassive black hole. So here's our video. See the little slug around? And that huge plume that's coming out, and then the plume that's coming back in to accrete onto the black hole. This is what we think happens when a star gets ripped apart from these tidal forces. So this is a simulation. This is what we think is happening. But what do we actually see, and how do we find this on the sky? So one of the kind of the new frontiers that's been expanding, especially recently in astronomy, is the transient sky. So what that means is taking images of the sky every few nights and looking for what changes. People have been doing this for millennia to look for things in the sky, right? This is how people figured out that there are planets that were different than stars, by looking at these differences over time. But these new transient surveys take this to kind of new levels and finding really, really faint things that just kind of blip in and go away over days to months to years. So how this works is you take images of the same patch of sky where you know what it looks like. So if nothing is happening, you would see kind of the same thing. But if something changes, then you can detect it and try to figure out what it is. So this is a real example. So here's a galaxy. It's not pretty. One of the reasons that these pixels are so big, why it looks so kind of blurry, is that helps with the precision of the measurement. But here's what we call a reference image. This is something that we know what it looks like. So then if you take a new image, you can subtract it off. And if there's nothing there, you should see just kind of a blank background. So in this image, they took a new picture and found nothing was different. But you keep doing this every few days for years over as much of the sky as you can. And eventually, you might find something like this. So here's a real detection of one of these stars being torn apart by black holes. This was done by a survey called Assassin. This is Assassin 14 Li. And so they found this little dot, and they kept following it up for actually several years to see kind of the event get brighter and then dimmer. But okay, so you say, how do you know that this was the tidal disruption event? This is just a dot. And the important thing for trying to find what these things are is to look at the light in a different way. So what we need to do is get a spectrum. So what a spectrum is we're taking the light from that little blip and spreading it out in color. So you can think about this like the Pink Floyd prism, or like sometimes when you see light coming through little bits of glass, you see little rainbows. This is the super high precision version of that. You take the light from the little dot, you spread it out, and you see how intense the light is by color. So here's an example for that event that went off in 2014. We knew what the galaxy looked like before. It looked like this kind of black line. And then when someone took a spectrum of the object again after it brightened, it looked like what's shown in red. So that kind of bright little blip that's happening in the green there, we can use that to tell us something about what the event is. And this will look very different than, say, a supernova, a star exploding, or something else. So we can do this. So we have all these surveys that act to try to find these new events and then go back and get spectra or images in the X-ray or the radio and try to figure out what these things are. So what do you do when you know what the event is? Well, one of the cool things about studying these supermassive black holes is we can tell something about the environment that they're in. For example, we think a lot of supermassive black holes at some point in their lives join up with other supermassive black holes. When two galaxies merge, they have two black holes and they eventually will kind of spin around each other and collide. But this is really hard to see, right? We're not going to see any light from those black holes. But if you send a star in, you're basically sending a bunch of debris into something. It's kind of like if you have a laser show and you send up a bunch of dry ice, the dry ice helps you see the laser show. That's kind of like what these stars do to black holes. So I'm going to show another simulation. This is what we expect to happen, given what we think the physics is, when you send a star into a system with two supermassive black holes. This is one of my favorite simulations. I just think it's really pretty. So you see it's gotten disrupted by the one, and then the rest of that star, that plume, that debris, is now being interacted with both of these black holes. And you see this big kind of complex debris field emerge. And the rate at which matter from the stars is falling onto the black holes will change how bright this is in this really complex way that we can try to then connect back to models like this to say, what went on? Why did that, that event with the star getting shredded look so weird? Can we match it to something like this? And you can see this is extraordinarily complex and something that is still an ongoing area of research in trying to find. But yeah, this is one of my favorite pretty simulations.
I'll ask one question about this. We had an AstroOnTap a few months ago about chaos for those who were there. Is there any of that going on here, or does it just look complicated? Yeah,
absolutely. So I wish I had the other video. I have a video of this that shows not just the star getting disrupted, but the star, if it comes into the system. If you have two black holes and then a star, you wind up with something called a three-body problem, which I think you guys might have talked about if you talked about chaos, where you can't write down just a solution with like one equation for how that works. You can't write down an analytic solution to how the system will behave. And you'll wind up with something that's kind of like a double pendulum, maybe you talked about, where you wind up with some chaos. This is getting a different, this is also having some of that same behavior, where you can't write down on one simple equation what's happening, which is why you need to do the simulation. You can't predict kind of what that final shape will look like that's on the screen. You have to run the simulation and say, like, step by step, what's happening? How is each of these pieces interacting with all the other pieces? Similar to weather on Earth and things like that. Cool. So
thanks.
Yeah, go ahead.
I just said thanks.
So what's next? Well, I think this field is on the cusp of a lot of really, really exciting discoveries. And that's because there's a new facility that's coming online, hopefully within the next few years, called the Vera Rubin Observatory. This is going to conduct something that's called the Legacy Survey of Space and Time, or LSST, which is like a backronym of a backronym. But LSST should start in 2023. That will probably be later because of the global pandemic. But what this facility will do will survey the entire sky to deeper depths over the whole sky that I can see from Chile. And what we've been finding, now dozens of these stars getting shredded by black holes every year in the past few years, which has improved from one or two when I started in grad school. This facility, the Vera Rubin Observatory, is going to find thousands of these events every year. It's going to find a fantastic amount of transients as well as asteroids and lots of cool stuff. So definitely stay tuned. You should start hopefully hearing about discoveries from that, especially here at Illinois, in the next few years. So with that, I will end and take any more questions that you've got. So thanks, everyone.
All right, thank you very much for that great talk. Yeah, we have plenty of time for questions, so please go ahead and type in the chat. We already have a couple here. Let's see, one from AstroOnTap CU. Do we ever see tidal disruption events happening between two stars or a star or a planet, or is it only between a star and a black hole?
Yeah, so it's often hard to tell what the object that got disrupted was. If it was a star and a planet, because the planet would be so much less massive than the star, it'd be really hard to tell kind of the influence of the planet on top of the star. But that said, we do expect to see kind of double disruption events when you have two stars, especially if the stars are in a binary that fall in at the same time. So there's some predictions going around that if you find an event like this where it gets brighter and then dimmer and then brighter again, maybe a year later, and then dimmer, that might be because there was two stars that fell in. So there's a lot of ongoing work in doing these kind of simulations to say, how do you tell that apart from something like the dual black hole scenario, or something weird about how the debris is falling in. But yeah, we do expect to see these kind of double two stars falling into a black hole scenario. Yeah.
Great. Mm-hmm. And another question, how long do these transients last?
These are bright for a few months. They're detectable for like several years. So they last like a little bit longer than a supernova. But for example, there's some tidal disruption events that were first observed in the early part of this decade that are still detectable, especially in the radio. There's, especially if you already know where to look, even though they're very faint, there's still some emission that's coming from some of these, a decade later. But they're the most bright for a month or a few months.
Thanks. And another question, is the star always entirely destroyed, or can you have a partial TDE that leaves the star intact?
Yeah, you can definitely have a partial TDE. And we expect, so there's been a few events that, for example, if you look at the total light that was emitted, you can try to use, equals MC squared. And what we expect, the maximum rate for matter to fall into the black hole, to say how much mass fell in to generate that light. And some of them, it's not very much mass. Some of them, it's, a 30th or whatever of the mass of the sun. So an example like that, we expect that maybe the star was actually mostly intact at the end. Maybe it was just a little bit of mass came off the star. We especially expect to find that if, say, the star has like a really grazing incidence with the point at which it would be disrupted. If just kind of a little bit of the star is kind of pulled off and then it escapes, especially if it's then kind of adjusted in its orbit by interaction with other stars. It could come and lose just a little bit of mass and then escape mostly unscathed. So we definitely expect to see this and probably have.
Okay, great. A couple other questions come in, one from Amelia. I think there was a fairly recent flare associated with the Milky Way's supermassive black hole. Do you know if that was associated with a star or with a gas cloud, and how might we be able to tell which is more likely?
Yeah, so there was this cool event that happened, I want to say now, I think that was in 2016, around the year now, but 4 or 5 years ago, where there was this cloud called G2 that was heading towards our own supermassive black hole in the Milky Way. And there was a lot of debate over whether this cloud would be disrupted and then kind of fall onto the black hole or not. And actually the cloud came out the other side mostly intact, which was not what people expected. And so so there's been a lot of debate since of what that is and why that happened. And we think that's probably because there's actually a compact object like maybe a neutron star, or a very low mass black hole that's in the center of that gas cloud, that's kind of providing enough gravity to protect against that tidal force. But let's see, as far as so that's kind of its. There's still a lot of debate over what that is. As far as flares from the supermassive black hole, you can see these flares when, say, like a star falls in. But black holes also accrete gas. They're not picky about what's falling in. And so many black holes accrete gas at a really high rate. So if you've seen other talks about quasars or active galactic nuclei, those are black holes that we can see kind of the energy from that accretion disk from continuous gas accretion light up the black hole, basically. For the Milky Way doesn't have an active black hole. There's not a ton of gas that's accreting around it, but there is a little bit. So especially like in the infrared, we see flares that would be exceptionally hard to see around, supermassive black holes in other galaxies. But around the Milky Way, because we have, such a great vantage point, we do see these little flares from gas accretion at very low levels from our own supermassive black hole.
Great, thanks. I'm glad to see a couple more questions coming in. One, is it possible or do supermassive black holes ever accelerate a star fast enough that the kinetic energy of the star destroys itself? Is that possible?
Ooh, so let's see. We do know that there's stars that we see on these really high velocity orbits in our own Milky Way. There's one example who I think Alex might be on watching on YouTube. He was on this paper, so maybe he can chime in the chat, where they tried to trace back the orbit of the star, and it seemed like it was maybe accelerated from an interaction in the nucleus of our galaxy. But the velocity is not that fast. Alex would have a more exact number. I want to say it was something like 10,000 kilometers per second. So not enough to do anything. The kinetic energy itself, when we think about the kinetic energy destroying something from moving fast, often we're thinking about the energy from something that's flying through like an atmosphere or something that's providing friction that would break it up. But without something like that, in the outer reaches of the galaxy, it can in principle go as fast as it could be accelerated. The key is getting it accelerated that fast. That's where really the limit is, where if you can accelerate it that fast, probably gonna be fine. But in order to get it accelerated that fast, there's a certain limit where it would probably just be disrupted instead of flung, if that makes sense.
Great. 1,700 kilometers per second, Alex says in the chat. So pretty fast.
Within an order of magnitude.
Another question from the other Alex. Could TD change the classification of a subsequent supernova, i.e. if the star's envelope is completely stripped of its hydrogen and helium layers?
This is a good question. Yeah, so if the outer layers got stripped off in a tidal disruption event, would that supernova look different? Probably, especially if, because a lot of the kind of what is setting our classification of the supernova is coming from what we're seeing in that outer envelope and what's around it. So I think so. I don't know if we've ever seen a supernova from a star that was previously disrupted. You have to think about like how rare is that in order for something to have this grazing interaction and then go supernova. What that means is that the star would have to have been formed and then be on that precise orbit within the several billion years that it would take to evolve from a massive star to a star that's capable of going supernova. But this is a good question. I don't know. I don't have a quantitative answer, but in principle, it's possible.
How would the spectrum change?
Oh, my other participant asks, how would the spectrum change? Yeah, so if you didn't have that outer envelope, depending on how much of it got stripped off, you would see, for example, like less hydrogen lines. But I don't know how much you can strip off and to what extent that changes what the supernova looks like. I'm certainly not an expert in supernovae. So you should also ask a supernova expert to see if their answer is different.
Great, thanks. And a couple more questions. So first, do you ever see these kinds of accretions from a neutron star onto a black hole?
Ooh, so for a neutron star onto a black hole, because the neutron stars are so much more compact, it's really hard to disrupt a neutron star because the in order for the tidal forces to rip it apart, it has to be that much different. The difference has to be really strong between kind of the one end and the other. So there's a limit on when we can see things being tidal disrupted around black holes, because if something has to get too close in order to be disrupted, it would, if that disruption is happening too close, it could be inside the event horizon, and that wouldn't be observable to us. So for example, you might think, more massive supermassive black holes should have more tidal disrupted events. But in fact, the opposite is true. And they wind up having fewer, because at a certain point, that radius in which they can disrupt stars is within the event horizon. And so for neutron stars, a supermassive black hole can disrupt it. We just would never be able to see it.
Great, thanks. And what happens with the rest of the star after the TDE? Does it just dissipate away, or will it end up clumping together and forming a new baby star?
Yeah, so it depends on how much of the star is disrupted. If really the whole thing is disrupted, like kind of these examples that I'm showing the simulations of and the artist's conception of, it will kind of, that debris stream will kind of keep falling in. So about half of the mass should eventually fall on, even if some of it kind of clumps together as it forms that disk that will eventually fall on. As far as the half that leaves, that has enough energy to kind of escape the gravity of the supermassive black hole, that mass is in principle then going to just be recycled in the rest of the galaxy. So if there's future stars that form near the nucleus of the galaxy, they'll have some of that mass